Greetings, Madam Shangari. I, Kevin Wong Shengyi from Group 7, Section 3A, would like to start our project's presentation on Newton's Law of Cooling. My fellow members are Harish Kumar, Hor Wai Keat, and Muhammad Haikal. For some context, Newton's Law of Cooling was first proposed by Sir Isaac Newton in his paper entitled Scale of the Degree of Heat. Our project studies the law through an experiment where we measure the temperature of cooling coffee over the duration of an hour under 4 ambient temperatures. The data collected were then analyzed using numerical methods. We attempt to close two research gaps, which are the limited research on the cooling of liquids and also the lack of application of the three numerical methods shown here. The 5 objectives of our project are to design an experiment to determine the proportionality constant, to apply numerical differentiation and curve fitting methods to determine rate of cooling and proportionality constant respectively, to study how ambient temperature affects the proportionality constant, and also to compare the accuracy of temperature calculated using the 3 second-order Wunsch-Kutta methods shown. Now I would like to pass the floor to Muhammad Haikal to continue the presentation. Thank you.
Okay, thank you, Kelvin. So I'm going to continue this presentation with question 1. So in question 1, we will have to evaluate the value of constant K, and there are several numerical methods that need to be performed. So first of all, we need to perform numerical differentiation of OH squared order. So here, we will need to calculate dt over dt. If you can see from iteration 0 to iteration 10, you actually can calculate it by using formula forward finite divided difference. And from iteration 11 and 12, you can using backward finite divided difference. And for the next part, here is the generated graph of dt over dt versus T minus TA, where A is the temperature ambience. So we are using Microsoft Excel to generate this graph. And the last part, we will have to perform a linear regression. So here our x is t minus ta and our y is dt over dt. So as you can see, we are using Microsoft Excel also to calculate y times x, y squared, st and sr. So the goal to perform this linear regression is actually to obtain the equation dtr over dt. So here we can see our dtr over dt is equal to 0.7404 minus 0.0656 times t minus ta. And once we obtain this equation, we can evaluate the value of k by using comparison with the original equation. So the original equation is dt over dt equal to negative k times t minus t. And first, we will have to expand this equation, and by that we can do the direct comparison. So for room temperature, our K is equal to 0.0656. And for the question 2, I will pass it to Wai-Chat. Thank you.
Thank you, Harry. I'm Hor Wai Keat, and I'll continue with question 2. So question 2, we have been asked to calculate the temperature of the coffee at time 30 minutes using ODE methods, which are Hume's method, midpoints method, and Ralston's method. So the condition given is at night, ambient temperature of 31.1 degrees Celsius, K equals to 0.0656, and then T initial at 91.3 degrees Celsius, and the time increment of 5 minutes. So as you can see at the left side, here is the differential equation after substituting the values given. And then the formula used for Hume's method over here. Then on the right is the results of calculated temperatures at time 30 minutes using Microsoft Excel. Then now we'll continue with midpoint method. Then as you can see, here is the formula used to calculate the temperature using midpoint method. Then here as well. Then on the right is the results of temperature at 30 minutes using midpoints method by using Microsoft Excel. And now we'll continue with Ralston's method. Over here is the formula used for Ralston method. And here as well, second equation, third equation. Then on the right is the results of temperature at 30 minutes. And now I'll pass it to Kelvin for the presentation of question 3.
Thank you very much, Wai Keat. Moving on to question 3, Newton's interpolating polynomials was selected as the alternative to regression. Firstly, a graph of temperature against time was plotted for the ambient temperature of 31.1 degrees Celsius. Then, a polynomial of degree 2 or a quadratic equation was selected due to its resemblance to the pattern of the graph obtained. Upon expansion, equation 1 was obtained, where B0, B1, and B2 are to be calculated. On the top right section shows the formulae and sample calculations for B0, B1, and B2, while the screenshots of the calculations in Excel are shown in the top left and bottom left pictures respectively. Upon calculations and substitution, the final equation obtained is shown in the bottom right section. Now I would like to pass the presentation to Harish. Thank you.
Okay, thank you, Kelvin. I will now present question 4. Okay, my name is Harish Kumar. Okay, basically for question 4, we need to find the K evaluation, but it's not different with question 1. The only difference is we have 3 types of condition. That is, we need to find in the morning, in the noon, and at the night. So now you will see in the morning. So the TA will be the 28 degree point 28.1 degrees Celsius. So the formula we may be using is numerical differentiation of OH. It's second order. And another formula we'll be using is linear regression. So the first formula we can see now is forward infinite divide differentiation and backward finite divided differentiation. So on my right hand side, there'll be a table. Next. Okay, from this is the evaluation that I get for dt over dt versus the graph versus TA graph. Next one. Okay, the following this calculation is actually using linear regression. So this on my right hand side, this is the formula that to use a linear regression to find that value, and my left side is from the Excel, the values from getting linear regression. Next slide. Next slide. Okay, and now we'll see at condition at noon. The ambient temperature condition at noon is 33.2 degrees Celsius. So the same method will find the forward infinite divided differentiation and backward infinite divided differentiation. Next. So we can see the graph of the dt over dt versus TA over TA dash TA, the temperature of it. So for the known also, we still use the linear regression form calculation. So at my left side is the Excel screenshot of the data that we perform using linear regression. Okay, next is in air conditioned room ambient temperature. There is TA. There is TA equals to 18.6 degrees Celsius. So basically the same formula will be used differentiation, numerical differentiation, which is forward infinite divided differentiation and backward infinite divided differentiation. So after we get the data, we'll do the graph using Excel. The next is also performing linear regression. My left side is the calculation of linear regression, and on my right hand side, on my right side is the calculation. On my left hand side is the data from Excel. So after we evaluate everything, we'll determine the K. To find the K, we need to compare from 1 to 2 with evaluation that value K, which is 0.0653. All right, now I'll pass to Harry.
Thank you, Harish. We are going to continue this presentation with discussion. And for question 1, once we have performed the linear regression and once we have calculate the correlation coefficient R and standard error of estimate, we can conclude that the obtained linear regression equation is not in the perfect line since R is equal to 0.9397 and it is not close to 1. As well, the data spread is not in a perfect line since our standard error of estimate is equal to 0.3724 and it is not close to 0. And for question 2, I will pass it to Wai Keat. Thank you.
Thank you, Harry. And now I'll continue with question 2. And in question 2, we have been asked how accurate is our answer compared to the measured temperature. So the measured temperature at 30 minutes is given by 45.6 degrees Celsius. And for Hume's and midpoints method, since the results that we get from Microsoft Excel are the same, so the true errors calculated is 1.9357%. And then for Ralston method, the true errors calculated is 7.8227%. So by calculating the true error, we notice that the percentage error of the calculated value using Hume's and midpoints method is smaller as compared to Ralston method. Therefore, it is closer to the measured value. And then now I'll pass the floor to Kelvin.
Thank you, Wai Keat. Now moving on to question 3, to answer the question of whether or not the answer from part 3 is the same as part 1, the equations obtained from each part was compared. After comparing, it is found that no, the answer obtained from both parts are not the same. There are 3 reasons for this. Firstly, it is because the subject of each equation are different from one another, where for part 1, the subject is the rate of change of temperature, while the instantaneous temperature of the coffee is the subject for the equation of Newton's interpolating polynomials. For better comparison, it is recommended that temperature and time was evaluated using linear regression in part 1. Secondly, there is a difference in the concept of each technique, where for linear regression, it takes a best fit curve which doesn't pass through all data points, while for Newton's interpolating polynomials, it takes all data points into account and it generates a best fit equation. Lastly, the types of equations for both parts are different, where for part 1, a first order differential equation is used, while for this part 3, quadratic equation was obtained. Therefore, there will be a difference in accuracy of values obtained from both equations. Now I would like to pass it to Harish to continue the presentation. Thank you.
Okay, thank you, Kelvin. So for question 4, the reason why we were trying to find this evaluation using a regression method is to find best fit from the data. But hence, since we could have using this using these three different method from morning, noon, and air conditioning room. But since these three could not find the perfect R and also the perfect line because the data is spread for all these three different method. So why it doesn't find the best fit line? Maybe it's due to the inconsistent of K, or also can because of the ambient temperature K is not constant. So maybe because of the temperature around the environment around the environment is not different, or can be due to human error also. That's all. So I'm going to present about the conclusion. So constant K value, we get the uneven values due to could be due to human error, or also the surrounding temperature also could play the role. Secondly, for ambient temperature of 31.1 degrees Celsius at night, K is estimated to be 0.0656. The varying rate of cooling with temperature can be expressed as dt over dt R equals to 0.7404 minus 0.0656 in bracket T minus TA. Thirdly, the linear regression value that we obtained did not meet perfection that we needed, as the R value is 0.9397. Also didn't get the perfect line since the data spread and sy/x equals to 0.372. Next, the relationship of the temperature with time was found to be using Newton's interpolating polynomials, which t in bracket time equals to 0.176 t square minus 4.02 t plus 91.3, which is different from the equation from part 1. The effect of ambient temperature on constant K calculation is inconsistent in real-time world. And lastly, Hune and midpoint method has the smallest relative error compared to Western method. So hence, the Hune's midpoint method has a better and closest value compared to Ralston's method.